For the past couple of years, TimberQuest has developed a GPU-accelerated weather forecasting system. This presentation will be covering the power of AceCAST for GPU-accelerated high-resolution weather forecasts. The presentation will begin with an overview of what AceCAST is and why a user may want to use it, then move into some performance benchmarks with regard to cost and speed. Afterwards, a brief case study will be covered, which looks at a 3-kilometer versus 1-kilometer comparison. Finally, the presentation will conclude with future outlooks for AceCAST. To start off, I would like to show this snippet of what TimberQuest provides. So, as it states, TimberQuest enables hyperlocal and low latency weather forecasts through the Weather Research and Forecasting Model, which is commonly known as the WRF model, on GPUs to create a faster time to solution, higher resolution, lower costs, and deeper insights. As already mentioned, AceCAST uses the WRF model using GPUs to accelerate a weather forecast. This results in faster time to solution, higher resolutions, and higher accuracy. In its current form, AceCAST can serve as drop-in replacements for existing WRF configurations. AceCAST is much faster than standard computing methods, such as CPU simulations, which means that smaller time steps can be used and greater awareness of localized weather can be sought out, which is typically missed by global weather simulations. Most importantly, AceCAST reduces the cost of a simulation. To see this reduced cost, we have created a test case with a grid size of 500 by 500 and a resolution of 1 kilometer. We ran this test case on 3 different processors, Xenon CPUs, EPYC CPUs, and NVIDIA A100 GPUs. Below we have 3 graphs. Each graph has 3 colors. The orange represents the EPYC CPU, the blue the Xeon, and the yellow the NVIDIA A100 GPU. On the left is a comparison of the simulation speed, which we define as the simulation time over the real time. In the center graph is the runtime, and on the right is a cost per run comparison. We note from the simulation speed graph in boxes 1A and 1B that one GPU is about 3 times faster than one CPU. For 2 A100 GPUs, these are nearly 2 times faster than 4 Xeon CPUs, which is shown in boxes 2A and 2B. When we look at the cost per run on the right, we can note that running on GPUs is about half as expensive as its CPU counterpart, and in cases even 3 times cheaper. This holds through about 8 processors. Beyond 8, the workload for a GPU, given the domain size, is not enough to maximize the resource efficiency. We can look at a case study that further shows the advantages of running WRF with GPU. So on August 9th, 2021, a severe weather event occurred in northern Illinois. A paper by Sabash et al. In 2019 has found that a 1-kilometer resolution within a convective allowing model can help in identifying tornadic convection. With this information, we ran AceCAST using V100 GPUs. We ran 12-hour forecasts using the 3-kilometer HER as initialization across multiple model runs and also downscaled to a 1-kilometer resolution and compared the results with the 3-kilometer counterpart. From the results, we saw that the 1-kilometer simulations did a better job at predicting a more conducive environment for mesocyclone development, specifically showing larger values southeast of Rockford, which is where 10 tornadoes were confirmed, of updraft helicity, storm relative helicity, and the energy helicity index. The figures below show the categorical outlook on August 9th from the Storm Prediction Center. Northern Illinois during this day was under a slight chance for severe weather and a 5% chance of seeing a tornado within 25 miles of any point. The upper level disturbance that was expected to move through in the late afternoon provided uncertainty in if and where tornado formation would occur. Now, if we take a look at the runtimes, we can see that the GPU simulations were faster than the CPU simulations. For the 3-kilometer simulation at a 500 by 500 grid, the 4 GPU simulation finished in about 3 minutes, where a 2 CPU simulation finished in about 14 minutes. For the 1 kilometer, a little bit of a smaller grid at 200 by 200. The GPU simulation finished in 25 minutes, whereas the CPU took about 4 hours. The GPU was over 4 times faster in the 3-kilometer simulation and about 10 times faster in the 1-kilometer simulation. Here we have the radar reflectivity. In panel A is the observed radar, and in panels B and C is the simulated column maximum radar reflectivity for the 3-kilometer and 1-kilometer simulations, respectively. Looking at the radar reflectivity, we note that the 1-kilometer excels in properly resolving the west and east cells, which are circled in black in each panel, that ended up spawning tornadoes in DeKalb County. On the left here is a SCUT sounding taken in central Illinois, showing that the general environment was highly conducive for supercell development. The storm relativistic values were also favorable for cyclonic updraft rotation. And if we take the most unstable cape, which from this sounding was about 6,000 joules per kilogram, and multiply that by the 0 to 1 kilometer storm relative velocity, and then divide the result by 160,000, we can get the energy helicity index. And if we do the math on that, that value ends up being 7, which is unitless, which also shows a favorable environment for tornadoes. Below are the storm relative velocity values from one of the simulations. On the left is the 3-kilometer, in the center the 1-kilometer, and on the right the ground truth, where the keys stand for where a tornado was confirmed. Comparing the 3-kilometer and 1-kilometer, the 1-kilometer does a better job at predicting higher pockets of storm relative velocity values, particularly in eastern DeKalb County, which is the red circled area, and western Kane County, which is the black circled area, whereas the 3-kilometer completely misses the higher values and predicts larger values elsewhere as broader ranges. A similar pattern was also observed for the updraft helicity, where the 3-kilometer completely missed any significant updraft helicity values that were captured in the 1-kilometer, and also confirmed through reported tornadoes, which is shown in the right figure. So in a nutshell, TempoQuest is the first known company in the world to use WRF and accelerate forecasts using GPU processors. AceCAST speeds up simulations, which allows for higher resolutions, deeper insights, and lower cost. From the case study, we've seen that AceCAST can accurately simulate high-resolution forecasts faster than CPU simulations. Additionally, AceCAST currently supports major WRF dynamics, physics, and nameless options. Looking ahead, TempoQuest plans to fully incorporate data assimilation techniques into AceCAST. Right now, AceCAST supports surface analysis and analysis nudging, and is actively incorporating spectral and observational nudging. TempoQuest also plans to create a hybrid WRF artificial intelligence weather forecast. In the figure on the right is a roadmap of TempoQuest divided into 4 sections. At the top is the GPU support, at the bottom the CPU host, on the right is the sector expansion, and on the left the NWP functionality. Today, AceCAST supports NVIDIA GPUs and will soon support AMD GPUs. We have customers in government, climate, and weather research, as well as operational forecasting, and are working with renewable energy companies. AceCAST supports the classic x86 Linux and Power architecture and is incorporating the ARM architecture. We are using WRF version 4 and are starting machine learning techniques, which will eventually transition to machine learning on specific data sets. For anyone interested, AceCAST is available right now. You can go to the TempoQuest website, just tempoquest.com, and download a free 60-day trial. We also have an online documentation technical website, which can be accessed by just searching AceCAST documentation. If there are any features that AceCAST currently does not support, but a user is interested in, we can incorporate any customization requests on a one-on-one basis. If you have any questions, or if you just want to say hello, please don't hesitate to reach out to us at support@tempoquest.com. Thank you for your attention. Here's a short list of the references used in this presentation.